Troubleshooting is the most challenging part of your job as an operator. Your know-how and experience are really put to the test when process problems arise. When a process disturbance comes up, there's a lot riding on how you respond. Slip-ups can lead to a wide range of problems: unwanted downtime, production and profit losses, the risk of damage to highly expensive equipment, and most important of all, workers could be hurt or worse. Yes, troubleshooting is a challenging, high-stakes exercise, and it's often frustrating and difficult. But done well, it can also be the most rewarding aspect of process operation. In this program, our goal is to develop a systematic, logical approach to troubleshooting industrial processes. In addition, the primary focus of this unit is the troubleshooting of processes or systems as a whole, not individual pieces of equipment within the process. We'll be investigating the kinds of examples in which a problem shows up in one part of a process, but the cause of the problem may be somewhere else. The challenge to you, the operator, is to zero in on the cause and bring things back to normal. In this first part of the program, we have three main objectives: to establish what we mean by troubleshooting, to break the troubleshooting process down into major steps, and to identify some helpful sources of information that operators rely on when they troubleshoot a problem. In simple terms, troubleshooting is the process of detecting problems, determining their cause, and correcting the problems. Granted, an abnormal condition could be simply a temperature or flow rate that requires only a minor adjustment. In this program, however, we'll be troubleshooting problems that are not as simple to figure out and correct. As you know, there's no magic formula for troubleshooting, no hard and fast, detailed procedure that's going to solve every troubleshooting problem every time. But the overall process of troubleshooting can be broken down into general steps that you can follow for just about all situations. For our purposes, we've divided the troubleshooting operation from start to finish into 5 major steps. The first step is identifying the problem and observing the symptoms related to the problem. This means determining that a problem actually exists. The operator becomes aware that there's an abnormal operating condition that requires a response. This is the process disturbance or upset that triggers the troubleshooting action. There are many ways operators are alerted to problems. Process variable indications may be off the mark, for example. Or you may notice abnormal operating conditions during a routine inspection of your process. An annunciator or alarm can also signal trouble. Some problems will cause the process to shut down automatically. In many cases, a problem will have more than one symptom. In any troubleshooting situation, there's an unexpected change in the process, and as we'll see throughout the program, the initial indication of this change can often provide clues to its cause. Once the problem is detected, the next step is to take the necessary preventive action, and this often has to be done immediately. That is, before you begin looking for the cause of the problem, you have to take whatever steps are necessary to prevent injury and safeguard equipment. What you do at this stage will depend on the problem, on the process, and on your facility's operating procedures. For some problems, you may have to initiate an emergency shutdown right away. Or, if conditions allow, you may be able to keep operating, but you might have to switch from automatic to manual control to investigate the problem. Another preventive measure that's sometimes necessary is to bypass a piece of equipment or part of the process while the problem is being looked into. Standby equipment may need to be used during troubleshooting. Process disturbances can have serious downstream consequences, so you may have to consider the possible effects of the problem before you start exploring its cause. For example, you may need to notify personnel in other process units that there's a problem in your area that could affect their operation as well. It may be necessary to make temporary adjustments to operating conditions to help prevent the process from getting dangerously out of control. This could involve actions such as reducing production rates, lowering temperatures, or changing flow rates within the process. Also, when there's an upset in the operation, it's often necessary to sample and test the end product to make sure it's of acceptable quality to sell or process further. If the product is off-spec, adjustments or changes in operating procedures may be called for. Depending on the circumstances, you may have to notify your supervisor of the problem. When the appropriate temporary safeguards have been taken, the next major step is to determine the cause of the problem. This step is the hard part, the real gist of troubleshooting. Logical deductive troubleshooting is essentially the process of elimination, separating factors that are not causing the problem from those that are or might be. We'll take a closer look at systematic ways of applying the process of elimination in the next part of the program. But before all the unlikely possibilities are eliminated, there are a lot of symptoms an operator can consider when determining cause. The particular characteristics he observes are often important troubleshooting clues. For example, is the change in the process abrupt or gradual? Or is the problem intermittent or constant? Is the affected piece of equipment one that's had similar symptoms and problems in the past? The answer to these questions can help the troubleshooter figure out the cause of the problem. Another thing to consider is whether the problem occurred while the process was in a steady state condition or was being started up or shut down. Sometimes a change in the operating conditions or environment can lead to problems in the process. For example, a recent change in the feedstock to the process, an increase or decrease in production rates, or even a sudden change in the weather. Each of these can be an important piece of troubleshooting evidence for the operator. No matter how an operator goes about determining the cause of a problem, he's going to have to fully understand his process. That is, it will be difficult, if not impossible, to figure out what's wrong with the process without knowing how it functions under normal conditions. An important part of troubleshooting is identifying what has been affected and what has not been affected by the problem. Normal process indications often give you as much useful information as abnormal indications. When the cause of the problem has been determined, the next step is to correct it. Correcting a problem can involve a wide range of possibilities, such as changing a process variable, or perhaps repairing or replacing a piece of equipment. After the necessary corrections have been made, the process will still need to be returned to its normal operating condition. For example, if valve positions were changed during the troubleshooting procedure, the valves will have to be reset to their original positions to return things to normal. Also, if the process was switched from automatic to manual control, when the problem is taken care of, it will need to be switched back to automatic. If the upset has affected other processes or units in the plant, you have to let them know that things are back to normal, so they can make adjustments at their end if necessary. As we've seen, an operator should follow a systematic procedure to troubleshoot a problem. To help guide him through this procedure, there are a lot of sources of information he can rely on. Among the most important pieces of information are the process variable indications, both in the control room and from local gauges or indicators. Abnormal readings, alarms, or annunciators often can enable an operator to pinpoint a problem. You may also need to refer to diagrams of the process, lab test results, unit logs, or indications of process trends to help you discover the cause of a problem. In addition, other operators can often give you some background or insight that can be a big help in troubleshooting. Basically, when you're troubleshooting a problem, you want good, reliable information. You want it fast and however you can get it. In this part of the program, we looked at major troubleshooting steps and some common sources of information that troubleshooters rely on. Take some time now to look over the corresponding information in your text. When we come back, we'll examine some process of elimination techniques. When a problem arises, the troubleshooter has to find its cause. In large, complex processes, the cause can be difficult to determine. Troubleshooting is based on the process of elimination, ruling out the components that aren't causing the problem and separating them from those that are or might be. Effective troubleshooters apply the process of elimination in a logical, systematic way. In this part of the program, we're going to look at some basic process of elimination techniques that will work for a wide range of troubleshooting problems. Process troubleshooting often boils down to eliminating components within the process. One way to do this at the individual component level is to conduct simple input-output tests. As you know, most components in a process have process variables associated with them that allow you to monitor operating conditions. By referring to the process variable indications, you can check the condition of the process entering the component against the condition coming out. For example, if the inlet temperature to a heat exchanger is okay, but the outlet temperature is off, then there must be a problem in the exchanger. Using input and output tests as a troubleshooting technique requires that you know what normal and abnormal indications are for the equipment in your processes. We've just seen how input-output testing works as a troubleshooting technique for a single component in a process. You can apply a similar method on a larger scale through an approach we'll call bracketing. The goal of bracketing is to confine the problem to a certain process or part of a process. You establish the boundaries of the problem, and anything upstream or downstream of these boundaries is eliminated as a possible cause. Here's a simple example to illustrate this technique. We've divided a process into three major sections: a pretreatment section, a reaction section, and a recovery section. Let's say, for example, that the quality of the product leaving the recovery section is off-spec. This could be caused by a problem in any of these three sections. It's often the case that a problem in one section of a process can work its way downstream and produce adverse effects in the following sections. Now, if the composition of the feed material that's fed to the reaction section is good, but the product leaving the reaction section is not up to acceptable standards, then we've effectively bracketed the cause of the problem to somewhere within the reaction section. Here's another example of how bracketing can work. This represents a polyethylene process, which has two reactor trains running in parallel. This means basically that the two reactor trains are producing the same product and at the same rate, but independently of each other. The equipment is the same for each train, and both trains process the same feed material. If the product from one of the reactor trains is off-spec, but the product from the other train is good, then we've bracketed the cause of the problem within this reactor train. When the cause of a problem is bracketed within a certain section of a process, the next step is to narrow the problem down even more. Let's take a look at a couple of ways to do this. The equipment shown in this process includes a steam heater, a reactor, a distillation tower, and its associated equipment. This includes a reboiler, an overhead condenser, and an accumulator. The overhead product from the accumulator is passed through another condenser. As a hypothetical example, let's assume that water has gotten into the process and contaminated the overhead product. The water could be leaking from any of several sources: from the steam heater, from inside the reactor, from the distillation tower's reboiler or overhead condenser, or from the other condenser. Each of these possibilities can start a chain reaction of adverse effects that will get carried through the rest of the process. To locate the source of the problem, we can start at the beginning of the process and work toward the end, checking each component one at a time. Operating conditions should be normal until we reach the source of the problem. If, for example, there's a water leak in this condenser, the temperature, pressure, and other major process variables for the steam heater, the reactor, the distillation tower, and its equipment should be fairly normal. But once we reach the condenser, the water leak is going to contaminate the product. This contamination can be discovered through sample testing. When this abnormal condition is detected, we'll know we've pinpointed the problem to this condenser. Checking components in a process one at a time in sequence is sometimes called the serial method of troubleshooting. This method is logical and effective, but depending on the problem and on the process, it may be time-consuming. In some situations, you can eliminate possibilities faster through a troubleshooting technique called half-splitting. With this method, each time you check a part of the process, you reduce the remaining number of possible causes by half. We'll use a deck of cards to explain the half-splitting method. If someone picked a card from the deck and we had to guess it, there are 52 possibilities. So with the serial method, it could take us up to 51 guesses. But with the half-splitting method, we can reduce the maximum number of guesses to 6. Here's how. Is it a black card? Is it a heart? So we know it's a diamond. If ace is high, is it a 7 or lower? Is it a jack or higher? Is it a king or higher? Is it the queen? So it must be the jack of diamonds. As we just saw with the half-splitting method, each question or test reduced the remaining number of possibilities by half. The half-splitting method can also save a lot of time in the troubleshooting of industrial processes. It's especially useful for troubleshooting control systems. We'll use a reflux control system for a distillation tower to illustrate the point. In this system, liquid in an accumulator is refluxed to the tower to help control the top temperature in the tower. The control system is designed so that the level in the accumulator controls the flow rate of reflux to the tower. And the flow rate, in turn, controls temperature. The control system includes a level transmitter, which produces an electronic signal that represents the level in the accumulator, a controller, which produces a corrective output signal, an electronic to pneumatic or I to P converter, which converts an electronic input signal to a pneumatic output signal, and an air-operated control valve, which regulates the flow of liquid to the tower. For this example, we'll assume that there's a problem in the control system and that the actual level in the accumulator is known. We can use the half-splitting method to determine which component is causing the problem. Our first step in troubleshooting the system would be to test the output signal from the controller. This splits the system in half. If this signal is correct, we've ruled out the transmitter and the controller as possible causes. Next, we'd split the remaining two components in half by testing the input air signal to the control valve. If this signal is what it should be, we know that the control valve is the problem component. You'll find that when it's applied the right way, the half-splitting method is much faster than component-by-component checking. It's also true, however, that the examples we just saw are fairly straightforward and simple. In other situations, processes don't always lend themselves to such neat and clean divisions. Also, the half-splitting method assumes that each test point in the process is equally convenient and accessible, and that may not always be the case. The rigid demands of a troubleshooting method may have to give way to practical considerations. The goal of troubleshooting is to apply the process of elimination as quickly and efficiently as you can, and we've tried to show you some ways to do that. Which technique works best will depend on the process and on the particular problem you're faced with. Up to now, we've been looking at general concepts of troubleshooting. When we continue, we'll begin applying these concepts. We'll start investigating specific troubleshooting examples. For the rest of the program, we're going to look at specific troubleshooting examples concerning specific industrial processes. The goal of the examples is to illustrate general principles and techniques of troubleshooting. You may or may not have direct experience with the kinds of equipment and processes you'll see in these examples. But even if you don't, you will be able to apply the basic troubleshooting approach and underlying concepts to the processes you operate. The first example involves a wastewater treatment system, a system that's used in many industrial facilities. Before we investigate a particular troubleshooting problem, however, we need to describe in general terms how the system works. We've divided this particular system into 5 major sections. The wastewater first enters the system through a collection section. This section typically includes a sewer that routes the wastewater to the rest of the treatment system. After collection, the wastewater is treated in stages. The wastewater from each successive stage of treatment contains fewer impurities than the wastewater from the previous stage. The first stage is called primary treatment. In general, the function of this stage is to remove quick-settling solids from the wastewater and to separate out unmixable materials such as oil. The next stage is called intermediate treatment. The purpose of intermediate treatment is to eliminate dissolved and finely suspended solids. The next stage of the system is secondary treatment. In this stage, organic material is decomposed and removed. Organic matter can occur naturally, or it may be a result of industrial operations. The final stage is called tertiary treatment, or in some facilities, advanced treatment. In this stage of treatment, both organic and inorganic impurities must be removed before the water is discharged to the environment or reused. Wastewater treatment systems also have a means of handling sludge, which settles to the bottom of the water, and scum, which forms on the surface of the water. Sludge handling and scum handling occur as part of the primary, intermediate, and secondary stages of treatment. The problem in this wastewater treatment system is a fairly common one: a high sludge blanket level in one of the clarifiers. A clarifier is a device that removes suspended solids from the wastewater. The sludge blanket level is basically the level at which the sludge on the bottom of the clarifier meets the liquid. The sludge acts as a filter to trap suspended solids in the wastewater. If the sludge blanket level is too high, the clarifier may not operate properly. The result could be solids carry over and insufficient removal of pollutants from the wastewater. In this system, there's a clarifier in the primary, intermediate, and secondary treatment stages. In this case, it's the clarifier in the secondary treatment stage that has the high sludge blanket level. A high sludge blanket level is the type of problem that, once it begins, it tends to work its way downstream in the treatment system. The sludge in the secondary treatment stage is activated sludge, and this affects some of the preventive steps needed for this problem. Activated sludge contains microorganisms or bugs that eat organic material in the wastewater. Since in this case the problem was first detected in the secondary treatment stage, let's take a closer look at this stage. The wastewater from the primary stage enters the secondary stage through this line, and it's sent to the next stage of treatment through this line. This is an aeration basin, where air is mixed with the wastewater and with activated sludge. Oxygen in the air is needed to stimulate the activity of the bugs in the activated sludge. And this is the secondary clarifier. In this clarifier, the bugs and the sludge they feed in are separated from the wastewater. Most of this activated sludge is recycled back to the beginning of the secondary treatment stage. This sludge is known as return activated sludge, RAS, and the process of returning it to the clarifier is known as recycling. The sludge that's removed from the secondary clarifier but not recycled is sent to the sludge handling process. This sludge is waste activated sludge, WAS, and the process of removing it is known as wasting. The proper recycling and wasting rates have to be controlled to maintain the proper sludge blanket level, and ensure that the clarifier will remove enough of the suspended solids. In fact, a high sludge blanket level is often caused by insufficient recycling or wasting, but the rates are found to be normal in this case. The recycling and wasting rates are okay for normal conditions, but since there's a high sludge blanket level in the secondary clarifier, the amount of waste-activated sludge that's removed may have to be increased to bring the level down. Adjusting the recycling and wasting rates is a temporary preventive step that can take care of the sludge level for the time being. But we still need to discover what caused the high level in the first place. Before determining cause, additional preventive measures may also be necessary in the last or tertiary stage of treatment. Before the treated water can be reused or discharged to the environment, it has to undergo a process known as final testing and adjustment. One function of this process is adjusting the pH level of the water. The pH level should be near neutral before the water can be safely discharged. A high sludge blanket level in an upstream clarifier can affect the pH level, so the pH may have to be adjusted to make sure the water can be sent on. In extreme cases, discharge to the environment may have to be stopped entirely, and the wastewater would be recycled through the treatment system until the problem was taken care of. When the necessary preventive measures are completed, the next step is to figure out the cause of the problem. We indicated earlier that a high blanket level in a secondary clarifier can be caused by improper recycling or wasting of the activated sludge. But these variables were found to be normal, which eliminates this possibility. The operator also sees if the clarifier itself is working properly. If it's not, the sludge level could build up. But he finds it to be functioning okay, so the problem must be elsewhere. The high level could be caused by introducing water with a high solids content into the treatment system. In other words, if water with a high solid content is drained into the plant's collection area, the solids will get carried through the treatment system and eventually build up in the clarifiers, increasing the sludge blanket level. But by checking with other operators, it's determined that there's been no significant change in the water that's fed to the system. The solids content has been fairly consistent and normal. Before we decide how to proceed, this is a good time to check our progress so far. Since the condition of the wastewater fed to this collection system is normal, we can rule out the collection area of the system as the cause of the level problem downstream. The problem was first detected at the secondary clarifier, so we can eliminate the equipment downstream of that, the tertiary treatment stage. We also check the recycling and wasting rates of the activated sludge, as well as the operation of the secondary clarifier. So we can rule out the secondary treatment stage too. So at this point, we've confined or bracketed the cause of the problem to somewhere within the primary treatment stage, or the intermediate stage. This still leaves us with a lot of equipment and possibilities remaining. But at this point, we can cut the potential amount of work in half by applying a variation of the half-splitting technique. We can do this by checking the sludge blanket level in the primary clarifier. If it's normal, the cause of the problem is likely somewhere in the intermediate treatment stage. If the level's too high, the cause must be in the primary treatment stage. As it turns out, the sludge blanket level is high in the primary clarifier. The operator also notices that the clarifier itself is working properly. This means we can eliminate all the equipment in the intermediate stage and concentrate on the primary stage. In this system, the primary treatment stage includes screens, pH adjustment equipment, and the clarifier. As we said, the clarifier was found to be operating normally. The screens remove large solid particles and debris from the wastewater. If a screen is clogged, the solid material can get carried on through the system and increase the sludge level in the downstream clarifiers. An operator inspects the screen and sees that its cleaning system is not working. When operating normally, water is sprayed through the screen to wash off the solid material or trash that's trapped on the screen. But the sprayer has stopped working, and because of this, the screen has gotten choked with debris. It's discovered that a pump for the spraying system has shut off, so water is not being pumped to the screen. This is determined to be the cause of the high sludge blanket level that was first detected in the secondary clarifier. The problem with the pump has to be reported, and the pump will need to be repaired. In this system, however, there is a standby pump that will work until the other pump is repaired. With the standby pump on, the screen cleaning system is put back in operation. The sprayed water keeps the screen free of solid debris that could otherwise be carried through the wastewater treatment system. If you recall, when the high sludge level was first detected, some pH adjustments were made to allow the water to be discharged to the environment. With the problem solved, the pH may now need to be readjusted to the original value. Also, the sludge recycling and wasting flow rates for secondary treatment will have to be checked once again and returned to their previous values if necessary. And of course, the operator will keep an eye on the clarifier sludge blanket levels throughout the system to make sure the screen repairs corrected the problem. In this segment, we used a specific operating problem to represent a general troubleshooting approach. Or, to put it another way, we use the process of wastewater treatment to illustrate the process of elimination. And this is the training strategy we'll be applying for the rest of the program. We also saw that there's more to troubleshooting than just spotting a problem and correcting it. Taking preventive action and, once the problem is solved, returning the process to service are also crucial to the overall troubleshooting procedure. Take some time now to read and study segment 3 in your text. Then, when you're ready, we'll move on to another troubleshooting example. In this part of the program, we're going to continue investigating troubleshooting examples. The example we'll look at in this segment concerns a pulp mill. But once again, the deductive troubleshooting techniques we'll see will apply to other process industries as well. A pulp mill is part of a process that makes paper. The operation generally consists of 3 major sections. The first is a wood yard, where the wood is received, stored, and in many cases, broken down into smaller fragments called chips. The second is a pulp mill, where the wood chips are then broken down into fibers and mixed with water, forming pulp. And the third is a paper mill, where the wood fibers from the pulp are formed into a sheet, which is shipped as paper. The problem we'll be looking at centers mainly on the pulp mill. There are different types of pulping processes. The type we'll be dealing with is called the kraft process. Let's see basically how this process works. The first of the major parts in this process is a digester. The digester is a vessel in which the wood chips are softened by a combination of chemical solutions, high temperature, and pressure. This process is known as cooking. In this example, the heat and pressure are supplied by circulating steam through the digester. Next is a refiner, a device with rotating discs that shred the chips into pulp. The refined pulp is then passed through a screen. The screen removes chips that are too large to be used in paper-making processes. And finally, a washer removes chemicals from the pulp by displacing them with water. For simplicity, we've shown only one refiner, one screen, and one washer. There's usually more than one of each of these components. In this example, the problem is first detected through sampling of the pulp coming out of the washers. The operator sees that there's a high debris level in the pulp. This means that the pulp is dirty, with long, thin black material in it. A high debris level creates a substandard quality of pulp. This could eventually lead to problems in the paper mill, such as an inferior quality of paper. Since there's a problem with the pulp, changes may have to be made in the paper mill to make sure that paper will be of acceptable quality to sell. That is, the paper mill may have to change their final product to one that isn't adversely affected by a high debris level. They may have to switch from making one type of paper product to another. A high debris level can be caused by any of several possibilities, and in any one of the three major sections of a pulp and paper process. For example, it could result from improper operating conditions in the paper mill. Debris removal equipment in the paper mill may not be operating properly, but in this case, the problem was spotted in the pulp before it entered the paper mill, so we can eliminate the paper mill right away as the probable cause. The source of the problem could also be the woodyard. If abnormally large chips are sent from the woodyard to the pulp mill, it could lead to a high debris level in the pulp. In this mill, there are chip screens that screen the abnormally large chips. The screens are checked out and found to be working properly. The chips sent to the pulp mill are of normal size. Since the pulp mill is receiving normal-sized chips, we can rule out the woodyard as the cause of the problem. At this point, we've bracketed the problem within the pulp mill. In the pulp mill, there are several factors that can cause a high debris level in the pulp. It could be a bad screen, perhaps, with a hole in it that allows debris to pass through. Or it could be a refiner with worn discs, which don't shred the wood fragments enough and leave too much debris in the pulp. The problem could also be abnormal operating conditions in the digester, such as improper cooking or poor steam circulation. When troubleshooting, you'll often find that some parts of a process are easier and more convenient to check than others. You don't want to invest a lot of time and effort inspecting one component only to find that the cause of the problem is another component, and one that can be inspected quickly and easily. In this example, inspecting the screens and refiners would require that the equipment be shut down and taken apart. But you can get a good idea of operating conditions in the digester by simply referring to the process variables in the control room. So the operators will check the digester before they try the screens and refiners. Also, the digester can be checked out without reducing production rates or shutting down the process completely. This brings up another rule of thumb about troubleshooting. If it's possible to do so without violating any safety guidelines, it's better to try things first that enable you to keep your operation going. In addition, it's harder to troubleshoot a process once it's shut down. Your company's operating procedures will tell you when the process must be shut down to avoid damage or injury. This operator is conducting a K-number test. This test is applied to a sample of the pulp to determine the amount of cooking that occurred in the digester. A normal K-number reading means that the chips were cooked for the proper time and at the right temperature. A high K-number, however, indicates that the chips were undercooked, and a high K-number is consistent with a high debris level in the pulp. The K-number is found to be normal in this case, but this still doesn't rule out the digester as the cause of the high debris level. As we said earlier, poor steam circulation in the digester could also lead to a high debris level, and it could do so without necessarily affecting the K-number. One way to check the circulation is by referring to the process variables relating to the steam flow in the digester. Sometimes there's a trapped air pocket in the digester that impedes steam flow circulation. The air pocket can also create false pressure readings in the digester. The pressure and temperature readings are checked, and a discrepancy between the two is detected. The discrepancy could be caused by an air pocket. To pursue this possibility further, the digester's pressure control valve will be inspected. This valve bleeds air and non-condensable gases from the digester at a certain pressure. But if the valve is not working properly, air pockets could get trapped inside the digester. Further tests confirm this theory. The actual valve position is not what the control system is calling for. The pressure control valve is found to be dirty and sticking. For this problem, cleaning the valve corrects the situation. To do this, however, the appropriate safety procedures for isolating, inspecting, and repairing the valve had to be observed. When the control valve is put back in operation, digester conditions have to be monitored to make sure the circulation problem does not recur. The steam flow, pressure, and temperature indications should be normal. In addition, the debris level of the pulp leaving the washer will be checked again to make sure the pulp is up to specifications. The operators in the paper mill will also need to be informed that the debris level is back to normal. They may have to make some adjustments to resume producing the type of paper product they were making before the problem arose. In this part of the program, we saw how the process of elimination was applied to a problem in a pulp and paper process. We also saw how the major steps of troubleshooting were followed from beginning to end. After you've had a chance to review this information, we'll look at a troubleshooting example for a different type of process. In this part of the program, we're going to investigate the troubleshooting of a problem in a refinery process. More specifically, we'll look at a problem relating to a catalytic reforming unit. Although we'll be looking at a refinery process, the basic troubleshooting method we'll follow also applies to other kinds of industrial plants. Before we begin looking at a specific troubleshooting problem, we need a brief description of the process. Catalytic reforming converts a charged material, usually naphtha, into a higher octane product called reformate. To do this, the charged material is exposed to heat and pressure, and it's passed over a catalyst inside a reactor. The reformate is used as blending stocks for motor fuels or for petrochemical feedstocks. To identify the main components in a catalytic reforming unit, we'll use this simplified illustration. There are a lot of different pieces of equipment in the unit, but for simplicity, we can divide most of the process equipment into three major sections. We'll call this the reaction section, this the condenser section, and this the separation section. The reaction section consists mainly of furnaces and reactors. The furnaces heat the charged material to the proper reaction temperature. In the reactors, the reforming reactions occur, which convert the feed material into a higher octane product. The effluent from the reaction section is basically a mixture of heavy liquids, light liquids, and gases. The amount of heavy or light product in the reactor effluent is determined partly by reactor temperatures. The higher the temperature, the greater the percentage of lighter product. The lower the temperature, the greater the percentage of heavier product. This reacted product has to be condensed before it's sent to the separation section. The equipment in this section includes two condensers, a fin fan type condenser and a shell and tube type condenser. In the separation section, the gases and lighter liquids are separated from the heavier liquid product. In this section, there's a product separator and a type of distillation tower called a stabilizer. The main function of the separator is to remove gases, mainly hydrogen, from the product. The hydrogen is passed through a compressor and mixed with the feed entering the unit. The purpose of recycling the hydrogen is to protect the reforming catalyst from the effects of carbon deposits or coking. Carbon attaches to hydrogen instead of to the reforming catalyst. The amount of hydrogen that's recycled is normally held constant. Any hydrogen not needed for recycle is removed from the unit. This hydrogen, called hydrogen make or export hydrogen, is used elsewhere in the refinery. The flow rate of hydrogen make is monitored and controlled. From the separator, the liquid product is sent to the stabilizer. In the stabilizer, the gases and lighter liquids are separated from the heavier liquids and removed. The heavier liquid that's removed from the bottom of the stabilizer is the reformate, the end product. In this example, the first indication of a problem is an increase in the hydrogen make flow rate. By checking his readings, the operator learns that this increase has been sudden and abrupt, not gradual. A preventive measure that should be taken is to check the downstream conditions of the process. An excessive conversion of liquid to vapor could also cause product yields to be lost and the quality to be lowered. Downstream processes should be alerted. If the reformate is off-spec, it may have to be routed and stored in a different area than normal until the problem is solved. Also, an increase in the hydrogen make flow rate means that more of the light gases are exported elsewhere in the refinery. The processes that receive the exported hydrogen will have to be informed of the increase so they can make the necessary adjustments in their area. A high hydrogen make flow rate can be caused by any one of several factors, but a systematic way to investigate all the possibilities is to think in terms of the major sections of the unit and eliminate the possible causes one section at a time. In this particular case, the problem is first detected at the hydrogen make flow indicator, so the problem is confined to the equipment upstream of the product separator. This means that we can eliminate the separation section. In addition, although the hydrogen make is high, the hydrogen recycle rate is checked and found to be normal. So the recycle compressor is working properly and can be eliminated as the cause of the problem. This leaves the rest of the equipment in the reaction section and the condenser section. We'll start by checking the process variables in the reaction section. A good place to start is by checking the reactor temperatures. If they're too high, too much of the product is converted into light gases, and the hydrogen make flow rate will go up. That's not the problem here, however. All reactor temperatures are normal. In addition, the operators investigate the other process variables in the reaction section, and all indications are normal. This means we can rule out the reaction section. So at this point, we've effectively bracketed the problem within the condenser section. The problem could be either the fin fan condenser or the shell and tube condenser. A good way to proceed is by checking temperatures for these components. If either is too hot, it could result in not enough gas being condensed, which in turn results in a high hydrogen make flow rate. Since we've got two components to deal with in this section, we can apply some half splitting and check the outlet temperature of the fin fan condenser first. This temperature is in fact too high, so the problem has now been narrowed down to the fin fan condensers. These are the condenser fans. After a closer look, it's discovered that one of the fans has stopped. And there's the problem. The fan motor has shut off. Without the fan, the product is not being cooled and condensed sufficiently. The operator has the motor restarted. If it gets hot and shuts off again, he may have to get the motor repaired and cut back on the feed rate to the unit. When the fan motor is running properly, the operators will still need to make sure that the problem is fixed and that the hydrogen make flow rate has returned to normal. And if there was an adjustment to the feed rate during the troubleshooting process, it can be returned to normal. You may or may not have to operate a catalytic reforming unit, but for any complex process, when you're faced with a problem, a logical way to troubleshoot is to confine the problem to smaller and smaller sections of the unit until eventually you home in on the cause. Once again, it's a matter of applying the process of elimination in a methodical and deductive way. A good systematic approach will work for you no matter what process you're dealing with. As you know, industrial processes are operated to a great extent by control systems. These systems regulate process variables to maintain desired operating conditions and allow you to make a good product. When it comes to troubleshooting, however, you'll often discover that it's the control system that's giving you problems. One of the instruments in the control system may be malfunctioning. As an operator, you won't do much repairing or replacement of the instruments in your control system. But what you can do, using deductive troubleshooting, is determine that there's a problem with the control system. And once you've determined that, you can often figure out which system component is not working properly. In this final part of the program, we'll be looking at troubleshooting of process control systems. Control systems differ, and so do the operating procedures associated with them. When troubleshooting control systems, you'll need to follow your facility's procedures to make sure you proceed safely. The example we'll look at here is a control system that regulates a furnace's outlet temperature. This furnace heats a process fluid for a reactor. The outlet temperature of the process fluid is controlled by regulating fuel flow to the furnace. The furnace has several gas burners, and fuel to the burners is distributed through a header. The header gets its fuel from a main fuel supply system, which serves all the furnaces in the plant. The initial problem that's detected is that the outlet temperature is too low. If the temperature of the process fluid leaving the furnace is too low, it won't react properly in the reactor. The flow rate of the process fluid can affect its outlet temperature. If the flow rate is too high, the process fluid will not receive enough heat. In this case, however, the process fluid flow rate is normal. Another symptom of this problem is that the header pressure is found to be too low. For some reason, there's not enough fuel getting to the header. Also, the header pressure is not consistent with the fuel controller's output. The controller output is high, but the header pressure is low. The source of the problem could be at the main fuel supply, but in this case, the fuel pressure from the main fuel supply valve checks out. So the control valve that regulates header pressure is getting enough fuel. This is a good sign because it indicates that the problem is limited to just one furnace. While the problem is investigated, the control valve can be bypassed and the header pressure can be increased by operating the furnace under hand control. For this procedure, this manual bypass valve will be opened as these block valves are closed. This temporary step seems to do the job. Header pressure is brought back up to a normal indication. Shortly, the outlet temperature of the process fluid also returns to normal. Even though the outlet temperature is back to where it should be, the operators will still keep an eye on the process variables in the reactor and other downstream equipment that can be affected by abnormal furnace conditions. As you may know, a low outlet temperature for a furnace can be caused by any of several factors. But the fact that the furnace is working well when operated under hand control points to the fuel control system as the cause of the problem. In other words, at this point, the problem has essentially been bracketed within the control system. In general, when a system or part of a process operates properly in hand control, but not in automatic control, that's a good indication of a malfunction in the control system. To learn what components are used in this particular control system, we'll use an illustration. This system has 4 instruments: a temperature transmitter, which is a thermocouple in this system, a controller, an electronic to pneumatic or I to P converter or transducer, and an air-operated control valve. The thermocouple senses changes in temperature and produces an electronic output signal that represents the value of the temperature. The controller initiates the action required to regulate the outlet temperature. It does this by measuring the signal it receives from the thermocouple, comparing the signal to set point, and producing a corrective output signal. The I to P converter changes or converts the electronic input signal it receives from the controller to a pneumatic output. In other words, it converts current to air pressure. The converter is needed in this system because the control valve is air-operated. The function of this valve, as you recall, is to regulate the flow of fuel to the furnace and thus the pressure in the header. To determine which of the 4 components is causing the problem, we can apply the half-splitting method. The midpoint in this system is between the controller and the I to P converter. The output signal from the controller is what it should be for the present conditions. Therefore, a good signal is getting to the converter. So we can now eliminate the controller and the thermocouple. They're working as they're supposed to. This means the malfunction must be in either the converter or the control valve. The input air pressure to the control valve is checked first. This air pressure turns out to be too low, so not enough air is getting to the control valve to operate the valve properly. However, the output air pressure from the I to P converter is checked and found to be okay. This indicates that the system is losing air pressure somewhere between the converter and the control valve. The operator looks around for any obvious problems. Sometimes there's an air leak in the system. He discovers a leak on the discharge line of the converter. A loose nut is causing the air leak, so tightening it should correct the problem. The nut may have shaken loose over time as a result of vibration in the area. To verify that this corrective measure worked, the control system is tested. Some of the testing can be done while the furnace is still under hand control. For example, the operator can adjust the set point on the controller and make sure that the control valve operates like it should. If it works now, it should work when the furnace is returned to automatic control. Testing the system in this way also eliminates the chance that both the converter and the control valve were not operating properly. When the system is once again working normally, the furnace can be taken off bypass and returned to automatic control. When the furnace is back under automatic operation, the operators will continue to monitor the outlet temperature to make sure that the problem has been corrected. The example we just saw had a simple solution: correcting a loose nut in an airline. But it's often the little things that cause big problems. In a case like this, determining that the cause of the trouble is somewhere in the control system is half the battle. From there, it's often easy to apply a logical, straightforward approach to zero in on the problem component. In this program, we've looked at troubleshooting problems that had nice, tidy solutions and happy endings. But as you know, the real world doesn't always work that way. When you troubleshoot a process, you'll often try things that don't work and arrive at dead ends, even if you're following a systematic troubleshooting procedure. And on the other hand, some of the problems we've laid out step by step you may solve right away. With repeated experience handling similar situations, you'll become trained to rule out certain options almost by instinct. With an understanding of the basics we've presented, you'll have a good head start in the challenging but important job of process operations troubleshooting.